So far, we have discussed the technical limitations of the conventional grid. These were related to the physical infrastructure such as transmission lines, transformer, substations, and power quality. Now let us move to the second category of drawbacks, operational problem. You may have the best electrical equipment in the world, but if you cannot operate and monitor it efficiently, the overall performance of the power system will still be poor. Now you can think of a modern hospital. If it may have advanced medical equipment, but if doctors and nurses cannot monitor patient properly or respond quickly during emergencies, patient care will suffer. Similarly, a power system also requires continuous monitoring, quick decision making, automation, and real-time information. Unfortunately, the conventional grid lacks these capabilities. Now let us understand each operational problem each one by one. Now look at carefully this slide. You can see an engineer wearing a helmet and holding binoculars with question marks above his head. This illustration perfectly represents the working condition of the conventional grid. It is almost like trying to manage the power system while blindfolded. Now imagine you are driving a car. Would you drive with your eyes closed? Obviously not. You continuously observe the road, the speed, the traffic, and the fuel level. Only then you can drive safely. Similarly, electric utilities also need continuous information about the power system. Unfortunately, the conventional grid depends heavily on manual monitoring. Field engineers must physically visit substations, transformers, transmission towers, and distribution lines. They inspect equipment, measure electrical parameters, record observations, and then report the findings to the control center. This entire process is slow and labor intensive. Now imagine a distribution transformer located in a remote village. If its oil temperature suddenly increases, will the control room immediately know about it? No. Someone has to physically visit the site, inspect it. This delay increases the chances of equipment failure. This is why manual monitoring is considered one of the biggest operational limitations of the conventional grid. Many of you may have seen electricity department employees checking transformers or climbing electric poles. Why do they do this? Because the conventional grid cannot automatically send its health status to the utility. Everything depends on physical inspection. Now let's move to the second operational drawback, that is slow fault detection. There is something every electricity consumer has experienced. Suppose a transmission line breaks due to heavy rainfall or a transformer suddenly fails. How does the utility know that fault has occurred? In many conventional systems, they actually come to know only after consumer starts calling the complaint center. Instead of utility detecting the fault, the consumers inform the utility. Only then maintenance team begin searching for the fault location. This process usually follows several steps from receiving complaints to identification of fault. But in smart grid system, intelligent sensors continuously monitor electrical parameters. Whenever a fault occurs, the control center immediately receives an alarm, identifies the fault location, and initiate corrective action. Therefore, fault detection becomes much faster in smart grid. Now, suppose a tree branch falls on 11 kV distribution feeder during a storm. In the conventional grid, people first notice that electricity is unavailable. They call the utility. Engineers search for the fault. This may take 2 or 3 hours. But in smart grid, the feeder itself reports the fault location within seconds. Now let's discuss another important operational limitation, that is limited automation. Now, first, we will understand the meaning of automation. So, automation means performing operations automatically without continuous human intervention. Can you think of some example of automation? Just like automatic washing machine or automatic elevators, automatic traffic signals, automatic doors at shopping malls. Nowadays, automation has become common in almost every field. However, the conventional power grid still depends largely on manual operations. For example, switching operations, then load transfer, fault isolation, and service restoration often requires engineers to manually operate switches or circuit breakers. So, this process consumes time. Because of a limited automation, the conventional grid cannot respond quickly to changing operating conditions. Smart grid overcome this limitation by using intelligent electronic devices, remote control switches, SCADA, and automated control system. Then moving to the next point. Now you can observe the balancing illustration shown in the figure. So in this figure, one transformer is loaded while another transformer is almost idle. This is very common situation in conventional power system. Utilities often do not know the real-time loading of every transformer, feeder, or substation. As a result, some transformers continuously operate beyond their rated capacity. Other remains underutilized. What happens if a transformer operates under overload condition for a long period? Its temperature increases, insulation deteriorates faster, its life decreases. Ultimately, it fails much earlier than expected. On the other hand, another transformer nearby may be carrying only half of its rated load. This means that available infrastructure is not being utilized efficiently. Therefore, the utility has already invested money in electrical equipment, but it is not obtaining maximum benefit from those assets. Smart grid continuously monitor transformers loading and balances the load automatically, thereby improving asset utilization. So, another operational limitation is also lack of real-time data. Today, almost every application uses real-time information. Google Maps tells us traffic condition instantly. Then banking applications immediately display our account balance. Food delivery app shows that the exact location of the delivery person. Similarly, utilities also require real-time information. They need to know current demand, then voltage, frequency, transformer loading, breaker status, equipment temperature, renewable generation, and battery status. Unfortunately, the conventional grids provide very limited real-time information. Most data are collected manually or after significant delay. Without real-time data, utilities cannot accurately forecast demand, detect abnormalities, predict failures, or optimize system operation. It is almost like trying to drive a car while looking only in the rear view mirror. By the time information reaches the utility, the actual system condition may already have changed. So let's summarize the operational problem we have discussed. So the conventional grids mainly suffers from manual monitoring, manual monitoring. Then second, slow fault detection, slow fault detection. Then third, limited automation, limited automation. Then next, inefficient asset utilization. Inefficient asset utilization. And next, lack of real-time data. So because of these operational limitations, utilities take longer to detect fault, then respond more slowly during emergencies, utilize asset inefficiently, and struggle to provide reliable electricity supply. So these challenges clearly indicate the need for modern, intelligent, and automated electrical network. So far, we have understood two major categories of drawback. First, we discussed the technical problems such as one-way power flow, transmission losses, voltage regulation, and power quality issues. Then we studied the operational problems including manual monitoring, slow fault detection, limited automation, and lack of real-time data. Now let me ask you a simple question. Can a power utility survive if it continuously spends more money than it earns? The obvious answer is no. Just like any business organization, electricity utilities also need to maintain a healthy financial balance. They must generate revenue to pay for fuel, maintenance, employee salaries, equipment replacement, and expansion of the electrical network. However, the conventional grid suffers from several economic problems that increase operational cost and reduce revenue. Let us understand this problem one by one. So first economic problem is high operational cost. In the conventional grid, most activities are performed manually. Engineers regularly visit substation, technicians inspect transformers, maintenance teams travel to fault location, meter readers visit every consumers each month. All these activities require manpower, vehicle, fuel and time. Now you can imagine a city with 10 lakh consumers, electricity consumers. If each consumer has a conventional meter, someone must physically visit every house to record the meter reading every month. Now think about the manpower required for such task. Apart from meter reading, utilities also spend money on regular field inspection, manual switching operations, emergency repair work, equipment testing, preventive maintenance. All these expenses significantly increases the operational cost of the utility. In contrast, smart grid technology such as smart meters, then SCADA system, IoT sensors, and remote monitoring reduce the need for manual work and improve operational efficiency. Now you can think about the online banking. Earlier we had to visit bank for every transaction. Today we transfer money using UPI or mobile banking within seconds. Banks have reduced paperwork, manpower, and operational costs through digital technology. Similarly, smart grid reduces operational cost by digitizing the power system. Now, let us discuss one of the biggest challenges faced by electricity utilities, especially in developing nations. First one is the energy theft. Electricity theft means consuming electrical energy without paying for it. This can happen in several ways. So it can happen illegal direct connection from a distribution lines, then meter tampering, bypassing the electricity meter, unauthorized use of electricity. Suppose one person steals electricity, who ultimately pays for that loss. The utility cannot simply ignore it. Eventually, these losses affect honest consumers through higher electricity tariff. Electricity theft also increases what we called as aggregate technical and commercial losses. These technical losses occur naturally because of resistance in transmission and distribution line. The commercial losses also occur due to electricity theft, incorrect billing, non-payment of bills, or metering errors. So the combination of these two called is aggregate technical and commercial losses. Utilities always aim to reduce these losses because they directly affect the financial performance. In India, the state electricity distribution companies invest significant resource in reducing these losses through smart meters, then feeder monitoring, aerial bounded cables, aerial bundled cables, and digital billing system. So many smart grid pilot projects in India were specifically introduced to reduce electricity theft and improve revenue collection. Now moving to next part. The third economic problem is the billing inaccuracies. Most conventional electricity meters are electromechanical or basic electronic meters. These meters only record cumulative energy consumption. Every month, a meter reader visits the consumer's premises and notes the reading manually. Now imagine the challenge involved. What if the meter reading what if the meter records the wrong readings? What if a digit is missed? What if the consumer is not at home? What if the meter is inaccessible? All these situations can result in incorrect electricity billing. Sometimes consumers receive bills that are much higher than the actual consumption. Sometimes the utility receives less revenue because of incorrect readings. Both situations create dissatisfaction. Manual billing also delays bill generation and payment collection. So this affects the cash flow of electricity utilities. Smart meters automatically transmit meter readings to the utility. There is no need for manual reading. Billing becomes faster, more accurate, and more transparent. The fourth economic drawback is the high maintenance expenses. As we discussed earlier, most of the electrical infrastructure has been operating for several decades. Old transformers require frequent servicing, then circuit breaker require periodic inspection, transmission lines require regular maintenance, substation require continuous testing. Unexpected equipment failures increases repair cost even further. So all these activities involve significant expenditure. Moreover, emergency maintenance is always more expensive than the planned maintenance. The conventional grid mainly follows a reactive maintenance, where equipment is repaired only after failure occurs. Smart grid introduces predictive maintenance using sensors, then artificial intelligence and data analytics. Utilities can identify equipment deterioration before failure occurs. So this reduces maintenance cost and improves system reliability. Now you can think about servicing your motorcycle. If you service it regularly, the maintenance cost remains low. However, if you ignore servicing completely, one day the engine may fail, leading to very expensive repairs. So, the same principle applies to electrical equipment. So, let us summarize the economic problems of the conventional grid. The major economic challenges the transmission utilities face is the high operational cost, high operational cost. Then second, electricity theft, electricity theft. Then third, billing inaccuracies, billing inaccuracies. And next, high maintenance expenses. So this problem reduces the financial health of the utilities, increases electricity tariffs, and limit investment in the modern infrastructure. Therefore, improving the economic performance of the power system is one of the major objective of smart grid technology. So you can observe something interesting. Many technical and operational problems eventually becomes economic problems. For example, high transmission losses means more electricity must be generated. Generate, Generating more electricity requires more fuel. More fuel increases operating cost. Similarly, slow fault detection increases outage duration. Then longer outage requires additional repair work. Then repair work increases maintenance expenses. Therefore, all categories of drawbacks are interconnected. Smart grid addresses these challenges together instead of solving them individually.